Okay, welcome back everyone. In this segment, we're going to be talking about the electromotive force and then also energy and power in DC circuits. So last time we had sort of ended with the concept of potential difference, which we also call voltage, and now we're actually calling this EMF. So these are all names for the same thing. And so in the diagram here, you have two different types of batteries, a AA and a D cell. And you have a little resistor that these electrons are going through. And you can see that what's happening here is that there's chemical reactions that occur where electrons are transferred from one terminal to the other. There's a potential difference between these poles. And if you've studied chemistry, you'll know about electrochemical reactions. You might have studied how, for example, zinc plates and copper plates have a potential difference between them because of their electronegativities. And so what happens here is that negative charges are repelled away from the negative terminal of a battery and they move towards the positive terminal. Now in real life, we say, well, the electrons are moving in real life, but last time we talked about conventional current, which would be the direction that positive charges would flow, which are the opposite. Okay, so when we talk about the largest potential difference that a power source can have, this is called the electromotive force, or EMF. So this symbol epsilon here is not related to epsilon naught, so you have to be careful. It's a different symbol in different contexts. This is the potential difference from a power source. So it's not actually a force, it's the amount of energy per unit charge. It's joules per coulomb, or volts. And the analogy that we like to use is that circuits are like water flowing through a pipe. Okay? In order to get water to flow through a pipe, you need to have a pump. And in a circuit, the battery is like the pump. Okay? Sometimes the pump is just a difference in height. For example, a waterfall. If you have a waterfall, the water is flowing from high potential energy to low potential energy. And the same thing is true of electrons in a circuit. So there's a pressure difference with a pump, and you have a certain amount of flow per second. The circuit is very similar. You have a potential difference, or a voltage, and that causes electron flow, which we call current. So it's very important to try to think about it in these terms. Now, when you draw a circuit, we use certain symbols to represent different things. So this is a pretty standard set of symbols that you're going to see everywhere. And so this first one here is DC voltage. Okay? And if you have an arrow that goes through this symbol, it's a variable voltage source. So this is a battery, basically. This first one is a battery. Okay, next one is a resistor. Okay, and again, an arrow shows that it's variable. Okay, V stands for voltmeter and A is ammeter, and they measure, respectively, potential difference for a voltmeter and current for an ammeter. And we'll talk more about those in the coming slide. So in a battery, the long line is the positive terminal and the short is the negative. Remember that conventional current flows out of the positive terminal and into the negative, because again, we're talking about the flow of positive charge. The voltmeter and ammeter are special devices, and we will talk more about them a bit later. Okay, some other symbols that you might see is the switch. Okay, it looks kind of like this. Turns a circuit on and off, closes or opens it. The battery is very similar to this one up here. And you might see a light bulb. So a light bulb is a type of resistor. It's a device that converts electrical energy into other forms, like light and heat. So now we'll step back for a moment and we'll talk about electrical power. And this is the rate at which work is done. Circuits are a really good example of this because you can only have a battery for a while. So we get charged energy based on the amount of energy we use over a period of time, which is known as power. And this diagram here shows us kind of the schematic of how you actually get power to your house. Okay, so all of these things at the top, the power plant, the transmission lines, the high voltage transmission lines that nobody likes to live near, the power substation, these are all involved in distributing electrical power. And studying the transmission of electrical power is a course in and of itself. Okay, so you have a transformer which is going to, well, change or transform the voltage so that it's in a form suitable to get to your house. And finally, you have another transformer right before it gets to you. So you might be talking about a power plant that's producing originally megawatts of power, okay, which is millions of volts per second. But you're not going to need that much in your house. So these transformers will turn that extremely high voltage into the familiar 120 volts that you have in your home. Or if you're European, they use 220. So where does that come from? Definition of power is energy over time. Energy over time, which is units of joules per second. So if we can take our units of electrical quantities and rearrange it to get joules per second, then we have power. So voltage is joules per coulomb, right? And current is coulombs per second. And so if we multiply those, you get joules per coulomb times coulombs per second, and you get joules per second, which is what we're looking for up here, which is watts, which is power. So power is equal to voltage times current. Other power formulas that you can use, well, we start with P equals VI. Note that V equals IR, and this was Ohm's law from last time. We plug that in and we get I squared R. And because I is V over R, we can plug that in and we can get V squared over R. So these are all synonymous for power, okay? All right, so here's an example. So I like to play on my 3DS at times when I'm not making videos, and my DS draws 150 watts of power at 120 volts when it's charging, and it takes 6 hours to charge up fully. And that's probably close to right. I didn't check the exact number, I just made it up. So we want to figure out how much current does it use when charging, and then how much does it cost to charge for a day. So first of all, current is power over voltage because P equals VI. So that's just going to be 150 watts divided by 120 volts, and that's essentially 1.2 amps, right? If I divide by 30, that's 5 over 4, that's 1.25 amps. I can do math, okay? So then for the second part, if we want to calculate the cost, well, now what we're doing basically is cost is going to be equal to the energy that it uses times the rate. Now the energy will be power times time, because power is energy divided by time. So energy is power times time. Okay, so how much energy does this use? Well, it's going to use the power, which is 150 watts, times the time, but we have 6 hours, okay, but that's per day. So I want to multiply that by 365 days per year. So hours per day, okay, and so days will cancel out. And so that's my power, and this is my time. And then finally, so that's 328,500 watts, or if you want, it's simply 328.5 kilowatt hours. So notice that energy is kilowatts times hours, which is power times time. Okay, so finally, my cost is going to be that energy times the rate. And it's 10 cents per kilowatt hour. So I just basically multiply that by 0.1 and I get 32.85 per year. So that may not be a realistic example, but you get some idea of how to calculate this, okay? And that's actually the cost of a decent game. So I have to pay the cost of one game to power my DS for a year. I guess it's the price you have to pay. Okay, so next time we're going to start talking about different types of DC circuits, and specifically we'll get into series versus parallel. So we'll see you then.